Okay, I will move this one right now to the spin orbital interaction. Actually, right now, we put the electron actually into the medium if they have the charge, on the top and the deeply charged on bottom. So if you have the electron moving along this direction, you have the electron field and on the left frame. But if you see when they're moving, but if you put your observation frame on the moving electron, and then you see something like the positive electron move in this direction, negative electron move in this direction. So you will see this electron will observe the effective B field on it. So that one actually gives you some kind of the a way of some kind of the B effective field like this. And actually this is some physiological way to explain what is spin orbital interaction acting on the moving electron. And also another thing is that usually Kramer theorem we have in the absence of the external B field, we call time reversal symmetry, up electron and down electron, they move in the different direction. They should be have some degeneracy like this. But if you also have the space inversion symmetry, then you will have the things like this. You will have this twofold degeneracy. And the Kramer theory, this also implies, which means if your crystal don't have the space inversion symmetry, you don't have this degeneracy, which means you will have zero field spin splitting, and the up electron and down electron, the energy will be different. So space symmetry breaking will give you a zero field spin splitting. This is from Kittel. So actually, it's that the structural inversion. Usually, right now we have two kinds of the inversion symmetry, and one is the structural inversion symmetry. We usually confined potential will give you the Rashba spin orbital impact, and the Bach inversion symmetry actually of the underlying crystal structure will give you a dress house, spin orbital coupling. And anyway, philosophy of this one actually is that space inversion symmetry will give you spin splitting and the effective magnetic field, and then spin precision. So actually the Hamiltonian of this one is quite simple. You have the kinetic term and the Rashba term and the dress house term. And this is the K momentum and the coupling cross product of K vector and the spin operator. And this is Rashba form style. It's dress house form. And the Rashba is gate voltage controllable, but anyway, it's all material dependent and the way you build it. So if you see the Rashba and dress house model actually, and you can calculate the eigenvalue actually for Rashba only. If you can see the Rashba only, then you will see the eigenvalue something like this, and they have they have energy splitting for the Rashba up electron and down electron. If you see the Fermi surface in the 3 dimension, it's just like this. However, if you turn, this is a cross-section. If you see some Fermi energy label, you will see up electron and the down electron. They are concentrical circle actually to each other, and one inner and one outer. And this is a projection of the one certain energy. However, when you turn on the dress house, and the energy shape projection will change, and it turn out to be it is the final when alpha equal to beta, the energy plot is something like this. It turns out to be, if you observe like this, it's some kind of the SU2 symmetry. You have two circles shift up and down along the 45 degree. And so it's implied actually you can find special gauge to gauge out the whole things into a simple way. And it turns out to be you really can do that, something like this. You can remap the whole things in a free electron-like system, and you can have the SU2 system like free electron-like. And it turns out to be you can find a spin-dependent, non-abelian spin orbital gauge, something like this. And change your Hamiltonian from like this way to be a simple, new kinetic term. And under the field moment and also the non-abelian spin-dependent momentum. And under one is the background potential and depends on alpha and beta. So this one gives you a simple idea how the things will propagate on 2D electron gates. If you have an electron propagate on 2D electron, and usually when they're traveling a distance, then we'll give you a phase, actually only something like this. But if you have spin orbital interaction 2D electron gas, you will have the unitary, something like a spin operator, only operate on the spin electron, on the spin dependent. So beside the traveling phase, you also will rotate the electron. You can decouple the system to analyze and in a much simple, clean way. So then from this one, you will see the persistent spin helix. This one actually was also proposed actually by Professor Shousen Zhang, 2006. He proposed two ideas. One is the persistent spin helix. The other is the Topological Insulator. And persistence, at that time, you try to find some quantum states, room temperature and robust. And this one is also room temperature and robust. Because actually when alpha equal to beta, the structure suddenly behave like this. And it's striped and quite persistent. And if you see the whole thing is something like this. And also this is actually alpha equal to beta, something like in this way and this way. But when alpha not equal to beta, they are contour map were in the circular and the ellipse. The most important thing is that this persistent spin helix, when alpha equal to beta, your Hamiltonian and the spin operator are commute. So it's very robust, and it's also good. It's a good way to be a quantum unit to be operated. Actually, last year I asked Professor Shousen Zhang. I said, why you promote the Topological Insulator and don't promote this one? He mentioned about it because Topological Insulator, experiment people have done that, and he figured out he doesn't have enough manpower to do other things. So he almost dropped this one. But right now, still quite a lot of small groups try to do those kind of study. I myself actually have quite a confidence on this kind of things. Okay, the application of spin current actually will be spin polar current and spintronic. I think I mentioned this actually, spin transport torque. But I want to add one more point. Actually, when you apply a field on magnetic material, because of realization, the magnetization will always relate to the field direction. When you eject the spin torque, so you provide actually the spin torque to counterbalance the damping. So if your spin current density is small enough, they will still damp to the field direction, but in a slower way. If your current density is large enough, they will push the whole things in a different minimum station, so it will flip over. But one tricky thing is that if you adjust your spin current density equal to the damping rate, then what will happen? The magnetization will, just like normal precision, oscillate all the way in here. So they will just like this. And this is idea for spin torque narrow oscillator. So it's a good, gigahertz to terahertz oscillator. And it's not non-trivial and not easy to be achieved by the semiconductor technology. And also, if you change your strength of the field, because this frequency is proposed to gamma h, so it's easy to adjust actually by the external B field. Okay, I think I will skip here because of time limitation. Yeah, I think I hope I spent probably 5 to 10 more minutes on the last subject on topological insulation. The charge quantum Tor effect actually is 2D electron gas with the magnetic B field. Because actually, if you have large B field, because of the electron will, because under the influence of B field, they will have a close motion on the center of the material, but only on the edge they will have the conducting wave. And that one actually under the B field, and also they found actually they have an integer quantum Hall effect and fractional quantum Hall effect. And these two groups all got the Nobel Prize. And so quantum Hall effect actually something like that. You have some material, you apply a B field, and this B field actually introduce a band gap, and on the bulk region, and you have the valence band and the conduction band. And however, on the edge state, they have the conduction channel. So you have one edge state conduction channel. If the same things then apply, if you have the spin current right now here, so you have up electron go this way, down electron go the other way. Then similar things, you have if you can apply certain B field or other spin orbital interaction, or even the magnetization, then you should observe the similar things like this. So only the A channel will open. And the up electron and the down electron, just like the Kerma series, they should be, they should be one edge state for the up electron, one edge state for the down electron. So they will go like this one. Why they call the Topological Insulator? Because actually for the conventional conductor, even though they also can have the surface state or edge state, but when you have some perturbation, then band gap will open. However, for the Topological Insulator, because of time reversal symmetry and the protect, and so after perturbation comes in, they still will not open. They will still like this one. So why would they call topological actually is that if you have the conventional, you will get open. But this one is something like this. Just like, inside and outside will never see each other. However, for this kind of things, they go all the way like that. And but if you have one fixed Fermi energy, you only have one cross point for one specific spin orientation. But you have other structure like this. Then if you go like this, it is have all the cross point. You have the even cross point. For this even cross point, then it's like this one. You still will never see each other. But for this kind of one, in can turn upside down. So they call this kind of with all the cross point, they call the Topological Insulator. So that's actually is a more mathematical way they call the Z2 Topological Insulator. All those things I think later on have a different lecture way explained in more detail. But anyway, it's some conventional one. If you have one Fermi surface, you have the even number of the cross point. But for the Topological Insulator, only have the odd number in the KE moment things. But if you go to another thing, you can go to see the time reversal symmetry. And because actually time reversal commute with your Hamiltonian, you can express like this way. And the square operate twice actually on spinel, actually is give you -1. So actually the consequence is that the state actually on time reversal invariant momentum K and the K equal to pi over A actually on the edge, they are degenerate. So that is one of the main reasons actually they are so robust actually on any defect on the edge state, because it's impossible to have the Anderson localization. And this is an easy way to explain. It's just like topological protection is similar the way like the classical, the optical things. If you have the two thin film layer, if you one refraction in here, the other refraction in the bottom layer, and the two refraction come back, they destruct it. So with a certain thickness, you don't have the refracting line, you only have the tunnel line. In here it's the same thing, because actually you have only two-way left and further back. When you have up electron goes like here, you only have two possible ways to left and back scatter. One is go like this way, because your up electron always while you're going out, so you go like this way. The other way is go inward, and you always get this way. And when you backward, and these two channels have the about 2 pi, phase difference, so it's become destructive interference. So the only way for land is to keep going up for the edge state. Okay, if you apply a voltage on the, and people actually propose it's quite possible actually for those phenomena on the zigzag on the zigzag graphene narrow ribbon. Actually, if you apply voltage bias actually on that, you will see only the down electron move in this way, because high potential here, low potential here, and the up electron go this way, and the bias voltage will actually broke the symmetry. And this actually was first proposed actually by the Chang and Malik. And they mentioned the normal electronic state of the matter will be gap actually in the bar. The most important is gap in the bar, and also have the gapless A on the edge state, and that gives you the topological insulator. However, this one only can happen actually on the graphene with the spin orbital interaction, But usually, as we know, the graphene actually has quite a weak spin orbital interaction. However, if you use a Landau-Kalisch formalism to use the same Hamiltonian, just like the previous slide, then you will observe actually you do observe the spin accumulation like this on the 2H. So later on the Professor Shousen Zhang proposed actually Mercury, HZTE can propose this one. And because actually HZTE and the CDTE, the quantum wave, they have the inverted band. So you have the edge state will happen. And the edge state is gapless. And in between land, the quantum wave, the box state, actually still is open gap. So the main reason for this count is inverted. You have the edge state is gapless, and the internal is the gap open. And this one gap open only appear when you less than a certain critical length, a critical thickness. It's such like this one actually. You have the gap open less than something like 6 nanometer. And for the bulk actually HZTE, if you have the spin orbital interaction introduced, it also can have the inverted band. But however, for this count, you don't have the bulk gap, so you cannot introduce the topological insulator. But right now people think the strength, HZTE can let the bulk actually open the gap. So it's quite possible. Also, people have experimental evidence that the strength HZTE in 3 dimensions is also possible. But anyway, it's a lot of things. People have done a lot of things on this. Professor Shen Chun-Qing will give a lecture actually on how he proposed, to study the topological insulator theory. But anyway, robust phase is that we can use the 3-dimensional topology realized by stacking the 2-dimensional, topological insulator together. It's not possible. But it turned out to be impossible because they have the scattering in between the two surface states from the impurity, or even though they are too close enough. So people have studied the finite size effect, which means if your 2 edge state is too close enough, they will have the cross walk and open the gap actually in here. And so edge state, if they too close together, less than 200 nanometer, you still probably cannot observe the things. I think I will skip this. Yeah. Okay, 3-dimensional topological insulator actually was done recently, numerically, band structure, and also experimented by a lot of things actually from different groups, and quite a lot of contribution actually from the Professor Qi-Kun-Xue group. He will mention about things. And recently he had observed actually an enormous quantized Hall effect. Actually, we always know we have the quantum Hall effect trio. And people observe Hall effect, classical Hall effect, classical swing Hall effect, classical enormous Hall effect. And this Hall effect, enormous Hall effect, all identified by the Hall, and this by Hirsch. And quantum Hall effect actually was identified, and also, sorry, this is quantum spin Hall effect, quantum spin Hall effect, then quantum anomalous Hall effect, and identified by the Professor Qi. Okay, I think that because of time, I will just stop here. And quite a lot of other contents will be given by different professors actually in this talk, and such as super spin fluid and other things. Before I close, I want to show the one of the last slides I want to talk here. Yeah, I think that we just identify a peak of the pyramid. And this could be the most significant discovery in this century. That depends on how deep we can dip into the earth. So hope, all of you in here can join this hard-working digging process and can identify the whole pyramid can solve. And it's a real one, not a fake one. And thank you for your attention. Okay, I think we have the lunch box. So, yeah, so you can have lunch box and come back. 是在这里。